CAST is an initiative funded by the Andrew W. Mellon Foundation, which was established only 2 years ago in 2012. It's intended to foster at MIT the exchange among artists, scientists, and engineers, which actually has a long tradition at MIT. It's in our DNA. It goes back in some ways to the founding of the Center for Advanced Visual Studies in 1967. But CAST is here in part to provide a supportive framework for that kind of research and activities. We support artist residencies, cross-disciplinary courses, research programs, performance series, and this weekend, the first of what will be a biennial series of symposia, Seeing, Sounding, Sensing, which has been organized in part to explore the relationship between the arts and cognitive sciences. I'm delighted to recognize Caroline Jones from our History, Theory, and Criticism program, who is here and is one of the principal organizers of it. So Tomás Saraceno was the first visiting artist for CAST in the fall of 2012, and we're very delighted to be able to welcome him back this week. He will participate in the symposium along with two other artists, a major keynote by the eminent philosopher and sociologist of science, Bruno Latour, and about 20 other scholars from a whole variety of disciplines. Now, this bad news is that we're heavily oversubscribed. So if you're not already registered, I apologize that we can't admit any more people. We are live casting the symposium, however, and you can see the address here at the bottom, arts.mit.edu CAST Symposium. There will be a live webcast of all of the events, which start tomorrow at 1:30 and go through a culminating concert with the work of the sort of pioneer musician Alvin Lucier on Saturday night. So I hope you will join us in one form or another. So we're all the more delighted that we could have this pre-symposium program here tonight, this evening, as a kind of warm-up act, or maybe spin-off is a better word, given the context of what we're going to discuss, reverberations, spiders, and musical webs. First, I'd like to thank Brenda Muniapian, who's the director of programs here at the museum. She would normally welcome you, but unfortunately she had to attend a wake, but we have collaborated many times, and we're pleased once again to be working with her team on this CAST program. So this program continues a conversation and an ongoing collaboration begun when Tomás first came to MIT in the fall of 2012 and met, among many other people in various departments, Professor Markus Buehler, who is the head of civil and environmental engineering here at MIT. We're going to hear more about this evening, but first let me just say a few words about that before I give brief introductions of our speakers. There's a very famous line from Tomás's official biography that everyone repeats, and I can't help myself to do it again. Many of us who introduce him just can't help but repeat it because it encapsulates very well the spirit, I think, of his wide-ranging, exuberant, and speculative experiments, creations, installations. It goes, 1973, born in San Miguel de Tucumán, Argentina, lives and works between and beyond the planet Earth. It sums up a lot, really, about his work. Tomás was trained as an architect in Buenos Aires, Venice, and Frankfurt. He also spent a summer in 2009 at the Space Studies program of the ISS, the International Space University, at the NASA Ames facility in Silicon Valley. He does many elaborate experiments and installations. I'm just curious, did any of you visit his installation on the rooftop of the Metropolitan Museum of Art in the summer or spring of 2012? So this was called Cloud City, but it's really part of an ongoing series of projects, a project that's been underway since 2009, known as Cloud City, sometimes as Airport Cities. It's a combination of elements, drawings, prototypes, actual installations that envision a series of aggregated, floating, transparent, inflatable, bubble-like biospheres in the sky that would be propelled by wind and sustained by solar energy. Many of you might think of precedents for this utopian kind of vision, Jana Friedman's mobile architecture, his manifesto, Feasible Utopias, certainly Buckminster Fuller. Both of them and others were sources of inspiration. But his work is very wide-ranging, for he makes installations that also have the morphologies of soap bubbles, foam, neural networks, cloud formations, and spiderwebs. And that brings us to the work that we want to focus on this evening. And his common interest with Markus Buehler. They share a deep fascination with and research interest in spiders, or more precisely, the webs that they weave, and including the molecular structure of proteins in spider silk, their use as an interesting possibilities for developing synthetic building materials, and so forth. So Markus Buehler received his PhD in materials science from the Max Planck Institute for Metals Research at the University of Stuttgart. He also has a master's in engineering mechanics from Michigan Tech, and earlier had studied at the University of Stuttgart, where he's from. As I mentioned, he's the head of our civil and environmental engineering department. He directs the laboratory for atomistic and molecular mechanics at MIT. He leads the MIT Germany program, and he's a principal investigator on numerous national and international research programs. His primary research interest is to identify and apply innovative approaches to design better materials from smaller things, using a combination of high-performance computing, new manufacturing techniques, and advanced experimental testing. His scholarly work includes over 250 articles on computational materials science, biomaterials, and nanotechnology. He's received many awards. I'll only mention three. The Leonardo da Vinci Award, appropriately named, given by the Engineering Mechanics Institute of ASCE. The National Science Foundation Career Award, Presidential Early Career Award, it's the most highest honor that's bestowed on emerging scientists in their careers. And here at MIT, he's received an Edgerton Award, which is an award that we give to teachers for teaching and research for investigators in the early stages of their careers. So one of his publications I'd like to mention is a book, which he may refer to later, Biomateriomics. And what's so interesting about it for this conversation, and for those of us who are interested in the arts, is that it introduces a holistic approach to the study of biological and bio-inspired material systems. And he discusses in this book how art and engineering can function as mutually beneficial modes of discovery. And I think you'll hear a little bit more about that tonight. And I'm very pleased to welcome also John Oxendorf as our moderator. John has appointments both in architecture and is also in civil and environmental engineering. He's a structural engineer with a multidisciplinary research interests, including the history of construction, masonry mechanics, and sustainable design. He's was trained at Cornell, Princeton, and Cambridge University, and he conducts experiments on the structural safety of historic monuments and the design of more sustainable infrastructures of various kinds. He is the author of Guastavino Vaulting, The Art of Structural Tile. Having just returned from Barcelona, I'm even more intrigued by these amazing sort of tiles, structural arches. You may know that we discovered one in Massey Hall here at MIT when it was being renovated. And I happen to know that John promises lunch, a free lunch, to anybody who discovers a Guastavino vault anywhere in the country, and they're still being uncovered all the time. He has also received many honors. I'll simply mention the Rome Prize, Anna MacArthur. So thank you all for coming, and let me turn the program over to you.
Yes. Oh, thank you very much. Yeah, thank you. I'm kind of very, very happy to be here. And yeah, it's a little bit a challenge. Lila have very kindly asked me to somehow try to make clear what I want to say, which is not so easy because I get dispersed many times. This means I will try to focus and try to yeah, kind of start from some point and then let's see if I get a little bit to some other points. Does it mean, yeah, mostly, you know, when we talk about spiders, something which always surprised me is this is the type of spiders that everybody knows. And usually, you know, it's kind of an orb web, the garden spider, but there is other type of spiders. And somehow the webs also, you can divide it in a kind of a flat web, which might have a little bit of a variation in a three-dimensional space, but basically it's something which is very horizontal. But what I was all the time fascinated somehow is the spider which looks like a little bit more like this, which is a little bit more kind of a three-dimensional spider, you can call them. And this means it's a little bit like an idea of the type of spider which I was most intrigued. We'll come back later why it was interesting a little bit. Many of them are also kind of hybrid web, but we will try not to get there. This is kind of an early stage of the construction. Does it mean I will not now describe what they are? This is some of the artworks also I have been doing before, a little bit at the beginning in Venice, but a little bit the challenge, where we bought a black widow in Germany. You can receive it by post still. And then a little bit the challenge, which was, and I think so today particularly, I will try to talk, is like that we were trying to scan this three-dimensional spider web. Now what we find out is like there is not really a machine who can scan this web. I know that there are some bubbles inside there, but usually we run many times a spider web inside. Now the thickness of the thread is very, very thin. It's kind of 1,000 of a millimeter. This means there is no, it's very difficult to understand the emerging properties or the patterns of how, or kind of the geometry, how these spider webs are built. This means what we did, very simple. This means this was the problem, no? Is let's say we have a three-dimensional spider web, and we will try to understand how much and to measure every single segment of it. This means when we contact the Photogrammetry Institute in Technical University in Darmstadt, and then we set up this kind of a photogrammetry, kind of two cameras at the same time watching at one thing, and then, I mean, it was kind of complicated because it was very difficult to find a method how you could scan it. But basically, it was very simple. It was just kind of a simple laser that you could illuminate the web. And then when you take the picture, you can see exactly the intersection of the, here I have to stop 1 second, and we will try to get it there. 1 second. I don't need the sound yet, but if you want, we will look one of these. Yes. I mean, to give you an idea. This is when the laser is moving through the house where the web has been built, the spider is not there anymore, and then, you know, you can move it very slowly and you can see the intersection of the laser passing through the different part of the thread. How it's moving. Yeah, it's getting. And you can see where the spider usually lives. This is a black widow's web, and this is in the corner where she kind of goes to the retreat, and you will start to see kind of a funnel tunnel web in the corner. Yeah, there is getting on the right. There we are. Let me stop now this, and we go back to the other. Okay. This means we got all these kind of a very, very section of it, then we have to connect them together. Yeah, here are all these different type of threads. We didn't scan every millimeter. We kind of stop every 2 or 3 millimeters. This was a little bit. Then we got kind of a first three-dimensional model where you have all the kind of threads, so you somehow have to connect them. We could not find kind of a script to kind of extend and make it automatically. That I know that Zhao now is kind of improving, and then I think so we will get better and better on this idea of scanning. And then the other challenge was a little bit also to try to reconstruct it in a three-dimensional space. This means we got a map where we projected all the points on the bottom and on the ceiling, and then we got a little bit messy. we try to connect all the different links and threads. One of the things which was very, I mean, we were taking care, because when you have one thread here, then it's bifurcated in 2, then in 3, then in 4. That means something which is quite difficult, because, for example, the Black Widow have 7 different type of threads who have different types of elasticity and strength. This means how to keep all the time the node in space and how much tension you have to every single thread to keep the node in space kind of precise. This means we have these supplementary lines, and this is how we were connecting point to point without cutting them and putting everything in kind of a tension. And now we were kind of building. Yeah, this will get a little bit of a nightmare. And then, yeah, this is kind of the construction of the Black Widow, how when then was later cleaned. What we did is kind of upside down because it was much more easy. This means that arachnologists always kind of complain that it's upside down, but usually the spider is also hanging. This means why not so much trouble. Well, then later, you know, one of the collaborators, Peter Jäger, also, since was one of the first, the first 3-dimensional scan of Spiderweb, was presenting in a kind of conference and seminars, and this a little bit how, yeah, a little bit we also some other papers on the scanning. And then when I was at NASA, also at Ames, I met Gilles Clement also, and he said, well, Tomás, now that you have found a method together with other universities, why we don't send Spider to the International Space Station to try to see how Spider might, you know, have a difference between in my microgravity environment and here on Earth. This means we start to write together a paper, but always was missing somebody who can make sense of it, and you know, and try to understand. And this means when I got invited to MIT, and then I met Markus for the first time, say, oh, that's exactly the person who we were missing in the team, and hopefully we could start to work together towards the, you know, first we have to understand them here on Earth, for then try to see how different they are when they came back from space. And maybe, I don't know if I want to get here, but maybe I go quickly to this, Lila. Oh. But basically, I mean, the major interest, which also at the beginning, it got me into why of this kind of 3-dimensional spiderweb, because mostly of the astrophysicians, when they refer to the origin of the universe, was kind of the Max Planck Institute that ran something which was called the Millennium Simulation. And when always they talk right after Big Bang, they talk something about which is this cosmic web. And the analogy all the time they talk about it is this, it's similar to a 3-dimensional spider web. I mean, that was a kind of an entry point, which, you know, which was kind of funny, because everybody talk about a 3-dimensional spider web, but at the same time they never measure, or they never study it. I mean, it's kind of this very huge parallel of having something very, very close from far, but at the same time we didn't look too much of this thing. I mean, these are a little bit some of the things that we have been talking with Markus also, and you know, when we start to look at this is kind of the formation of the universe and how galaxies start to kind of condense and get together, and this is a kind of a, I mean, these are social spiders, no? Social spiders are the ones who live all together in one single web, and this is a little bit the analogy between both of them. And this is, you know, this is the first comparison. This is a scan on the left and the universe on the right. Right. Well, and then now one of the latest things that we are doing, we are also together with Molly Nesby in October, we will try to do a live concert of spiders. This means we have a very sensible microphone, and spider will play live in a concert. And I think so there is also like a lot of fascination, and also with Markus, then later we will see how he was taking all these aspects of the music and the spiders. Yeah, here we are trying to listen them. Yeah, while we're recording some of them. Well, and then just quickly, you know, some of the installation. This is in Düsseldorf at the moment, and where people could walk also suspended there. Well, I will not get so much in detail. But then I leave to Markus now the rest of the presentation. Thank you.
Thank you very much, Tomás. This is exciting. I'll show you a few slides, and I don't know if we can take questions. Any time, we like to have a conversation. And I actually am going to share some random thoughts with you, and maybe make you think and explore, and email me or discuss here. Have some lively discussion. What we did is we continued. We have had really, like Tomás, parallel lives maybe, and we had independent fascinations with spider webs of various kinds. And we met about a year ago, 2 years ago, a year ago, and it's been exciting since. And I'm truly thrilled. And today is special, right? I'm trying to share all the ideas with you and explore. We've done a couple of things. I'll go inside the spider thread, and I'll share with you what is inside these little threads, these many thousand millions of threads you've seen. But also we're going to go on the structural scale larger, and we show you how we connected his scanning experiments with the model we've developed. And Dr. Zhao Jin is here, and he will maybe do an interactive display, and the models, you can see it working live. So we'll have sort of interactive discussion and exploration here as we see fit. So we're fascinated because if you look inside the spider thread, so the web, one-dimensional, two-dimensional, three-dimensional webs are really interesting, intriguing. And it doesn't stop there, right? You go inside, you take a microscope, and you can see even more structure. So absolutely fascinating. The structure goes all the way down to the scale of individual atom. So hydrogen atom, carbon atom, and how they connect. And these scales of structure from the protein to what we call secondary structures, like beta sheets and alpha helices and things, go all the way through into fibrils and fibers and bundles and to the things you can see with your eyes. So what you see is not all that there is. There's much more inside. And we spent many years studying those structures and understanding how they're built, and how do we, as engineers, actually take the understanding we have from nature and build our own materials that are different and optimized, adapted for certain applications. So I'll show you a few things along those lines as well. So what if we have a science hat, we understand nature, but we also have the engineering hat and design new things and build them. And that's the connection with the arts, something I've been interested and fascinated by for many, many years. And it's actually making sense now. We can connect these in a meaningful way using mathematics and simulation and in other ways. So there's a really exciting opportunity for us here. This picture here shows you sort of future engineering, right? Today we have chemists that think about molecular structures, and we have structural engineers that look at this scale, and future structural engineer will look at all the scales. So the vision we have is if you construct buildings, infrastructure, we'll actually design the molecules. We'll design how the molecules assemble, how they come together at these different scales. And we can build, as Lala mentioned, we can build more from less. We can use the kind of raw materials we're not even using today. Today we use concrete and steel. They're very expensive, very energy intensive. In the future we can use rocks, we can use algae, we can have plants, and they can make materials that grow buildings, that self-assemble buildings, that have structures that can change dynamically. And the inspiration actually from Tomás is fascinating. Social spiders, right, that live in the space and they reconstruct the web. The web is changing. It's a living material, right? And so this is one of the directions that we're really excited about. And you can see where we're heading here, right? We're actually merging the biology, the structural engineering, the scales, and we're really interested in making nano big. So you've all heard about nanotechnology. It's very tiny, and I'm fascinated by this idea of making nano so big you can build cities and structures and infrastructure, roads, airports, and everything from that, and make them sustainable. So that's sort of the vision, but how do we get there? So we have discovered sort of principles. I'm very interested in understanding not only one material, one system, but making connections between multiple areas. And we use tools of simulation. We start from simulating the quantum mechanics of atoms and molecules, and we bridge them, we connect them with other materials. And so beautiful aspect of starting with quantum mechanics is you can simulate any material, right? So you can go and simulate spider silk, you can simulate elastin protein, you can simulate steel, concrete, and we can begin to compare how these different materials work. Right? And so this is what we put in a big box of knowledge and categorize how these materials function. And we move them into this abstract space. So we use mathematical tools to describe all these different materials. And they look very different, right? So concrete looks different from a spider web, but we have mathematical tools that allow us to identify similarities between them and commonalities and differences that define function. And so we've made these connections not only within materials and described how functional diversity comes from universality. So the idea that proteins are universal, these 20 letters or the DNA letters are universal all biology. But then we can make all these different functions, right? We can build motors from proteins, we can build spider webs, we can build adhesives in muscles, we can build the skin, we can build cells, we can build living organisms, all from the same chemical building block. And engineers are very far away from being able to do that, right? We sort of take a detour the brute force way by using all these different materials to create different functions. And biology has much to offer in creating different function from universality. So diversity in function from universality in building blocks. And that idea is intriguing to engineers, and we are sort of pushing the limits here and scratching on that surface and trying to design new things from that principle. And the other thing we'll talk a little bit later on is connection now to very different systems. And so we have this example here actually to illustrate to you how function emerges in proteins, right? Is the idea that you take letters of DNA or letters of proteins, which are 4 to 20 different kinds, and you assemble them in patterns, and you create new building blocks from that pattern, which again you can connect to new building blocks again. And actually you can combine different building blocks that are actually made from the same stuff, but they have different functional properties when they're arranged in certain geometries. And we can repeat this process many times and create a web. So this web actually achieves its function from a very delicate interplay of different scales. And we like to think of scale in a geometry space. But of course, function doesn't emerge in geometry space. It emerges in functional space. And so we actually, in the mathematical model, remove the geometry in the physical space from the function, and we see a synergy. So it's just like you have, simple example, simplistic way, you have 2 particles. 1 particle is pretty boring. 2 particles, they can interact. 3 gets more interesting. You have 20 particles. They can do very interesting things. They have phase transitions. They can be liquids and solids, right? So this is the same idea here. So each scale is like a particle, right? And you interact 1 scale, 2 scale. Engineers have 1 or 2 scales. We want to have 20 scales, 30 scales. So nature has, biology has 5, 7, 10 scales. And we can play with them. They can resonate, right? And so you create function at 1 scale, and you tune the knob at another scale, and a 3rd and a 4th, and suddenly you create this interaction, right? And so the way music emerges is the same principle. This is what we have here, right? So you have simple sound waves that you can modulate, creating the sounds of musical instruments. We then combine those into melodies. And so if you think in your head, right, how you emerge music that induces certain emotions, impressions, it's every little piece together. And suddenly you have this emergence of the feature, the property, right? And that is what happens in biological materials. Now, the connection actually is quite interesting. When we create music, and this is what I leave for thought and maybe discussion later, it's really a mirror. Humans have this interesting demand or vision that we like to continuously portray ourselves to the world, right? We make paintings, we create music, and it's actually really to show others who we are. And in the beginning, I think we made those paintings in the caves. We trying to explain to other members of our species how to hunt and how to do things. And in time, we created more complex functions and more complex pictures and paintings and music. And so we believe we can, and this is the thought for some out-of-the-box thinking, right? Can we use the existing creations of art, music, to study who we are, who we are as materials, because these structures, these complex compositions actually are created by our brain, by our bodies that are made from these physical structures. And so the idea that we're trying to explore is if we can use pieces of art to understand science, engineer, and actually sort of give artists who are experts in creating hierarchical structures. So music is a hierarchical structure. Ask the artist to design very complex pieces of engineering, which use a sort of different part of a brain than if you're an engineer and you think about your CAD program or you make a calculation. So we're trying to think outside the box, and we need the creativity and bring that in together. All right, so that's one thought, and we can discuss more later. So let me move on to the spiderweb again. So this is sort of why we do this, right? So we have many different thoughts that we're exploring here, in the work with Tomás, we began by utilizing these really interesting three-dimensional structures that he scanned, and we like to build models. And the reason, as I explained, we build models that start from the fundamental scale of atoms and molecules, and we can do analyses in a model in a computer simulation that we cannot easily do on a piece of paper or by looking at things. And so we can study structures, we can study functions, we can make changes to the web in a model, in a simulation that we can't easily do in a physical artifact. And so we're trying to utilize Tomás's experiment as a baseline to understand how the structure works. You can see enormous complexity here. And we don't understand how these structures are created and why they're created in that way, what the spider's objectives are in creating structures, how they built it. Right? Spiders built these structures in open space. Civil engineers, construction engineers use, what do we use? Cranes. We use scaffolding. Right? And spiders don't have any of these. So they somehow create a space-filling construct, very high complexity with tunnels and elements and planes without any of this help. Right? So we're trying to learn how they do that and why. And so we built what we did in the work, and we'll have a little illustration of the model in a few minutes. We took the data, and using our engineering and math skills, we translated the data that Tomás generated using laser scanning into a model. And we've done other models of two-dimensional webs, which is sort of the state-of-the-art in modeling or in understanding. And here we're pushing from 2D to 3D. Right? So the world sort of goes into two-dimensional graphene. We're beyond that. We're already going to the 3D. Right? we go from 2D to 3D and trying to build this model. So we've created this model, and you can see this is the installation piece that we had, and we built this model. And it's an exact replica of a computer model of this installation that Tomás did a couple years ago. And some interesting questions here in comparing that model, how it behaves with the computer simulation, how we can potentially, we thought about using a model in experiencing force through light or sound. So if you are a spider, you have different kinds of senses. And humans also, we don't sense force in a thread. So if you imagine jumping in a web, it's very hard to visualize, experience the forces, the strains, deformations in the web. And so we're trying to use the model to inform media like light or sound, maybe, in experiencing force, which is something we don't experience through light and sound usually. So that's some of the ideas we're exploring, right, in our discussions. And so connecting the web, scanning the web, bringing in a computer model, using the math and the simulation, extracting new information and bringing it back to the spider web, this live web. And you as a human or visitor can go in and experience that. And so that's one dimension of this. This is the model in a little more detail. And we can go and zoom in later with Zhao has some of those things later in a few minutes. Okay, so let me just show you a few more things. This is how the model looks like. So one of the strengths of the model is we can analyze systematically how this web is built. So you might look actually more random in the picture you've seen before, but we can analyze. We found these three regions, 1, 2, and 3, where the web is built in different patterns, which you don't easily see when you look at the three-dimensional structure. So that's kind of one simple way of explaining how the model can be used in extracting additional structural patterns and information. Right? We can slice the web in any way we like and inform ourselves in how it works. There's also interesting questions in how sound translates in this web, because spiders have a very keen senses in sensing vibrations, and Tomás mentioned the vibrations in the web, right? And so here we have actually a model now where we can compare these orb webs with the three-dimensional webs and sort of putting signals in the system and understanding how these signals travel, and comparing this 3D to 2D, also to a one-dimensional system of how we understand wave propagation typically is in a one-dimensional sense. And we know about wave propagation in a continuous medium, but in something like a web with extreme structural complexity and different scales and fractal maybe arrangements, we don't know anything or very little about how waves propagate and sound propagates. And so we think that could be again a way of visualizing an audio sense some of those vibrations in the model. I'm going to quickly show this here. This is the web, and I'm going to play this movie here. This is how it might take a few seconds. This is sort of a fly, a simulated fly, impacting this web, and that's sort of a simple exercise the model can easily do. We can understand how this web is deformed, how forces translate, and how vibrations translate, and how that web functions. There's a lot of work we can do with this. So we're just beginning to sort of explore this very complex system. So do you want to show, I don't know what we're going to do. I want to show some of the model in more detail. So Zhao, he's going to plug in. And maybe, can you connect to this computer here?
Yeah.
So I can continue. Yeah. So he's going to show, no, you can do it. Yeah. You do it. So Zhao has been working on this for about a year now, and actually in a very painful way, reconstructed this web in this computer model. Well, painful in a sense, developing an algorithm. We always develop the algorithms, but it was not easy because the data that we get from the scanning is very scarce. So it looks that's all connected, but actually there's a lot of defects and missing pieces, so we had to develop an algorithm to fit in these missing pieces. Yeah. So I let you.
Student and a high school student worked with me during last semester and summer to refine the structure. So we finally built up this computational structure based on what Tomás measured and scanned in his lab. And so here, the advantage of this computational model is you can zoom in, zoom out, and see how the structure for this web looks like. And then you can, because this model has the physical parameters, so we have the elasticity and the density contained in the model. So we can actually simulate if there's impact, how the web will deform and response to this impact loading at a single strand. So you can actually see how each of those threads get deformed. And actually, we also measured how this deformation as a wave propagates inside this complicated structure. And yeah, I think and yeah, you can simulate a lot of things. You can relate the frequency to some maybe use this frequency to compose a music or something relates to this. And also in this model we have the damping comes from the air. So if I continue run this simulation, so right now it's a very short piece of the movie. So if I continue, this oscillation will get smaller and smaller because the dissipation of the energy in the air. So Markus, do you want?
Thank you, John.
Okay, thank you so much. I'd like to invite you both up here, and I'm going to try to stay out of the way while these two brilliant gentlemen make spider music together. I don't know, Tomás, if you would like to go first and say anything in response to what Markus has shown.
No, I know, it looked like very simple, these, but it took us, I mean, and also Markus, when he said he was connecting the loosened threads and the losing point, I mean, it's like sometimes seems very simple, but And when I see it, it's like, I was there like connecting thread by thread and now putting back in the computer and see the simulation in the computer, because, my imagination when I see this is kind of, we're pulling up galaxies, right? That's the relationship with, and what I, what I kind of feel, and I like Markus' approach is this kind of, to push a little bit also the research that not only to breach the thing, but also to reach to the whole universe to a certain extent. There might be something there which still we don't know how it might be connected. But yeah, I don't know. And
And I guess for me, I would just like to say that this is a particularly special moment, I think, and to have it here at MIT and the combination of the creative with the analytical and the fact that simply what we're learning from you, for me, is spectacular. But Markus, would you like to add anything in response to, I guess maybe one question is, where to from here?
Yeah, well,
So what comes next? Now you
the
scanned a
universe.
laser web, a spider web, you've built a larger scale, painfully, because if you pull on one, 5 other ones go slack, and you had no model to help know how long they should be, and so that was very difficult. Could you imagine, now that you have models like this, perhaps pushing it in some new directions, or do you still feel like the spider is the master and they tell you what to build?
No, one thing that we kind of enjoy, and I think also Markus got really kind of both of us kind of enjoy more are these kind of social spiders. I think so that's something which, because the black widow is not really social to a certain extent, does it mean?
Yeah. The few that I've known have been very antisocial.
Yeah. But well, the degree of sociability also depends about how much space they have and how much food they have. Does it mean even if you have a very social, social spiders, they live all together in one single web until 10,000 species, and usually they have a kind of a huge web. Most of them live in Ecuador. Does it mean is they could be 3-4 meters big. And what they get is it like even they can catch like a huge prey. And also when they have offspring, everybody take care of the same as will be your child. I forgot what I was saying about it.
I think you were saying how special social spiders were, and that you wanted to consider, rather than studying just the webs of a single spider like the black widow, maybe there was more to do.
No, but what's not this,
if I could understand how your brain works, I would like to know.
Anyway, yeah, that's the. I will come back in one moment, but yeah, many of other samples. With Markus, what also will be very interesting. What we were thinking is how to turn this in a kind of musical instrument, and we have been also talking with Evan and Arnold about how also we could then beside being the spiders, being the players. Also how humans, maybe to a certain extent, we can learn. There is a kind of a pattern evolution of how the instruments also have been evolved through the capability of the player and how virtuoso they get it. This means since the beginning the spider were flat and the kind of two-dimensional world. Somehow the animals also, and there is kind of an evolution about the instrument and how good we learn how to play, and also how the instrument also kind of got more complex. This mean?
I'm not very knowledgeable of spider anatomy, but I think spiders cannot hear. Is that correct? Yeah. They cannot hear.
Yeah, but
so
it is supposed to be one of the more sensible animal in the world. One point was cockroach. Whoever knows more than me, please interrupt me. But and now it seems that spiders are very, very sensible, even if they are deaf. But all the exoskeleton vibrate. Does it mean even the hair that they are connected to the body somehow they can perceive a very, very, very thin vibration to a certain extent.
See.
Yeah, there we are.
So maybe one next step is in the direction of music and
yeah, exactly. That's what we are trying to
learning to play the web as an instrument.
Yeah, but also with Markus, what we thought, which was very important, also is like how kind of this let's call it instrument is built, right? This what could be interesting also is to because not you by tracking the animal movement, you cannot really kind of predict also how the web is. There is kind of a non-parallel thing because they build a lot of auxiliary. For example, William Heberhard, one of kind of famous arachnology also, he said, if you have to imagine that you have to build yourself a web as a human, you will be blind because most of spiders are blind, they don't see. You have to be under the water because this is the density that they feel the space when they move into the air. Is like yourself being under the water, blind, and building the web backward.
And presumably they never went to college, so they were just born with
and this
the
means
knowledge.
you have to imagine, it's like also, this means you are kind of standing here, and then you start to release a thread. No, you reel it out of the spinneret, and then you don't see, you're backward, you're in the middle of the water, you release the thread, and then the wind starts to blow, and you're kind of going fishing, but in the middle of the air, and then until they feel it, that got trapped because at the end of the line, they get some glue, and then somehow stick there. And this means by sticking there, they pull it back, and they see, they start to ting, 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 ting. This is why, this idea of the music all the time, they kind of sense it through kind of this vibration. How far is this? Because they don't know where it is, no? And then somehow cross into the middle. This is how I describe also the orb web, because that's the only one we have been so far studying. So they come to the middle, from the middle, go to the middle, and then, they have to find the middle point. Without seeing, and backward. It's kind of unbelievable. And then from there, they start to build a web. This is what we know about the two-dimensional web and the orb web. Now, how you got to, that's something which I think so. And this was never done, and this will be really something truly fascinating that we could explore together and try to find a way how we could do it, maybe.
Yeah. I guess I would just also like to add that as little as we understand about the natural world, the fact that the inspiration that you get as an artist and the inspiration that you're getting as a scientist and engineer are both coming from something so spectacular, yet little understood, I think is for me kind of fundamentally the kind of conversation we can have here at MIT, where we like to have artists talking to scientists and engineers. So that's absolutely terrific.
Yeah. No, I have been very cautious also, because otherwise I get too quickly. But most of these webs also, and maybe in the future, step by step, otherwise I get too quickly. But what I'm mostly working now is a hybrid spider web. That was really kind of fascinating. But
when you say hybrid, you mean different types of spiders working together on one web?
Well, but they will not. Now I come back to the idea of sociability. Exactly. Because it's very similar to the human, no? I mean, this means social spider, they're social. This means because they have enough space, enough food. But if you put a lot of social spiders in a very tiny space, then do not become social, they eat each other. This means pretty much humans, not to certain things. You have enough food, enough space,
like humans, yeah.
Then you behave. But anyway, they have a trend. And usually, for example, there are 43,000 species of spiders, and only 20 are social. This means very little. And even knowing that, knowing that sociability is a big trend to survive, let's say, on the planet Earth, nobody understands really how is this. And this means what we do is a lot of maybe try to make them cooperate and work one to each other, the solitary and the social or the semi-social, because there are some of the webs. Well, we can go back then to certain images, but what we do, a lot of experiments is like put first the solitary spider, she build a web, and we take out the solitary and we put a social colony of spiders. And they build the web on top of the other web. It's kind of using the pre-existing model to try to construct something together with different degree of sociability.
And they don't discriminate.
No, they don't live at the same time. They use, it's like me going to your apartment. You know what I mean? If you're social in the morning, well, we change during
You're
the
welcome
day.
anytime.
But how much I mess it up. This means some of the species, and we've been talking also with Markus, because some of the spiders, they eat their own web because they're proteins for them. Some of them, they do not eat the web. This means also some, they come there and they say, oh, the web is like a food, and they eat it up and then they build all over again. Some of them, they say, well, that's good enough, I build something on top. And then you can get very intricate webs, which is kind of more complicated to define where somebody starts and when somebody ends. That's what I'm trying to get.
Terrific. We're going to open it to the floor in just a moment, but maybe if I could just ask a little bit of history for you, Markus. At what point did you become interested in spider silk, and at what point did you learn about Tomás's work? Was it when he arrived here, really, that you learned?
Yeah, a little bit before he arrived. We've been interested in spider webs for a while. Became interested in proteins first, if you sort of proteins being the main building materials and things that we use, that nature biology uses to create function. And spiderwebs actually are one of the prototypes of an extreme function, which is extreme strength and toughness. Spider silk being stronger than steel, some silks. and actually much tougher because it's much more extensible. So it's imagining having a steel cable, a wire that you can stretch 50, 100%, right? And so that takes a lot of energy to break. So we took that as a prototype in the beginning as studying what extreme functions we can create with protein, which is protein is what you eat. Actually, it's if you have protein without structure, it's like jello. So it is not worth anything really in terms of mechanical strength. And so silk is one of the extremes there. But then we became more and more fascinated with larger scales and structures, right? We became interested with orb webs, and then Tomás, when he came, looking at three-dimensional webs, and a lot of times you like to expand on this, and so the ideas we have with going to space, and actually looking at how structure formation in this. So in a way, when the spider creates three-dimensional webs, it's like creating the universe, right? It's putting density fluctuations in material, and that's how we have this analogy with the early stage of the universe, right? And it's the spider puts material down, high density, there's low density, and out of these fluctuations emerge these complex features. So we're trying to go really big, because they're asking earlier where we're going now, and we're going to the universe. And trying to see.
Two very quick things, and then I'd love to hear from the audience. So think of your questions for these two researchers and designers. The first one is, when you began working together, was there a real problem of language? Because oftentimes when you come from different disciplines, you speak with completely different languages. And so, or did you pretty quickly understand, because you both are fascinated by three-dimensional webs, that you could understand each other?
I would say so.
Or is the common language German, and that's that?
Actually, we haven't explored that, actually. I don't know, but to us, it was very natural. I mean, there's a passion for the web and the structure and the intricacy. And the structure really was the common language, I think. And then we look at different functions. I mean, the artistic function, and for us, the mechanical and the biological. And but yeah, it's the structure. I think that was a common language.
No, it's
been easy.
Yeah, I mean, you understand. For example, Lilia today said, Tomás, don't start with the universe. You know what I mean? Start with something very practical. You want to start a web. Don't start with, don't start with a hybrid spider web, because then you confuse people. Everything gets simple, one step by step. You know what I mean? It's like I mix up too quickly, everything. You know what I mean? And then, and rather, I don't know if I can really make sense. I mean, it might make sense to a certain extent, but, it's like keep a little bit the peace that somehow also, we can kind of work together. It's like the social and the solitary, the engineer and the artist. You know what I mean? We might get.
I'm not sure which one's social and which one's solitary.
Doesn't matter.
And then just the last thing I wanted to ask is in terms of product of collaboration, because I find it fascinating that you publish technical articles and you have proposals to the International Space Station, and so in some ways you're operating as the scientist, artist, or...
Yeah, but it's unbelievable. I managed to convince some of them still. I cannot believe myself. Well, it's like in today with Markus here, say, you know what I mean? But
I think the work is pioneering and therefore worthy of being published. And so my question is, in terms of products, is it, for each of you, is it important to have an installation as a result, or are papers and creation of new knowledge the outcome of this? And maybe have your perspectives changed as a result of working together? I don't know. What do you think, Mark?
Well, for us, it's been really interesting to try to build some of the webs. We've built two-dimensional webs with 3D printing, and I didn't get to this, but with genetically engineered bacteria to make spider silk protein, and we've been trying to spin those proteins into webs and so forth. So we've been building it. So it's become really important as to build physical artifacts, two-dimensional ones, and so we're hoping now to make it three-dimensional. And having something you can go and walk inside and touch and feel is something really intriguing to me. So an installation like that, so that puts the model and the science engineering within the artistic expression would be absolutely fascinating. So we have actually discussed a couple of ideas in the last several days.
I should also add that in the world of MIT, where people publish a lot, Markus publishes an absurd, 40 papers a year or something. So I can imagine you're tired of writing papers and you're ready to build something.
That's right, yeah. Done paper writing, though. That's right.
No, I don't know what I can say, but because also with Evan and Roland, we start to talk about also like maybe the capability of Yeah, here we are. to the idea of maybe, you know, what it will take if also, you know, we kind of build some kind of web that also we could play. But, you know, I go back a little bit, you know, of the idea a little bit how I came also with this fascination maybe to try to incorporate sound to this installation and try to understand if spider, how they feel and perceive sense, no? And then we'll come with Caroline, you know, because they are deaf, but they can sense space with kind of a very, very refined technique that their own body is the one who vibrates. This means, you know, it's kind of go faster than the speed of sound. How you could, but you know, there is one book where it's called "Where Is Everybody," which is kind of a 40 answer to the Fermi paradox. Why we never enter or manage to communicate with somebody else. This means if you go to the moon, Mars, or far away, and you start to hear the planet Earth, it's kind of a noise. It's kind of you don't understand nothing. You understand it. It's like something. It's very difficult to understand. And one of the answers of this Fermi paradox is like saying, well, because we talk all different languages and we cannot somehow agree on saying or sending messages out of space. And it's mean a very simple answer to this is like, well, maybe we have to build an instrument that more than one person can play together. This means, to some extent, you know, it's this kind of instrument that spiders, social, non-social, are trying to build together, and then maybe we can start to tune ourselves to somehow start to communicate, maybe. I don't know if so far out of the planet Earth, but, you know, it's kind of an exercise to somehow to engage the capability to, you know, it's like it's very difficult if you play one single instrument yourself, and if it's an instrument that somehow is affected by the way somebody else play, like kind of a big drum, you know. When you go to a concert, everybody has his own single instrument. You have one instrument who somehow, you know, if we have a big drum, I don't know, 10 meters, you know, and everybody's hitting the same, you know, it's a little bit more something which affects so much the way how you play it also. I mean, it's kind of forcing a little bit to a certain extent to do. And you know, many of the installation also is something how we could learn to coexist to some extent, maybe to the perception of the sound in this extent, but I don't know.
I would just like to say the first time I met Tomás, I only understood about 10% of what he was saying to me. and yet, what I could catch was absolutely brilliant, and so I've enjoyed learning very much from you and your work. I would like to open it up to the floor and take questions. We are recording this event, and we ask that you speak into a microphone. And Meg has the microphone, and so you, young lady, are closest to the microphone, so you get to go first, and we'll go from there.
Thanks. I feel very lucky to ask the very first question. I think it's probably about something that I want to say about your point you made, which is how to take this further. So you were saying, you know, maybe social interactions and that kind of stuff. Maybe my question would be, this looks like a very kind of a complex system, and yet a dynamic one, of course, because it kind of it occurred across time. And perhaps I'm just wondering why we have like those finite discrete objects, which are those webs, and perhaps asking why you stopped looking at them at that moment, and perhaps asking whether you would see them developing over time, and perhaps what we're seeing here is an impact of a fly on this kind of system. That's fantastic, but how would you predict the kind of development of that web maybe across, I don't know, 10 years or 10 months? I mean, just getting the time back into the construction. And I think the music is perhaps addressing that point. I mean, just how to see this as a kind of dynamic, complex system, not one that's kind of a finite and ended in a way. I hope.
Thank you. So not a snapshot in time, but an evolution over time.
Yeah, we're actually, this is something we're trying to create now. I mean, now that we have a static model at one point in time, we were trying to build at one of the places, either in Berlin or here, the setup, and then doing the scanning over time. And actually, you raised an interesting idea. You know, when you imagine the web actually as a result, the structure of something happening potentially, right? There might be a fly, and that controls how the structure is formed. And understanding this sort of maybe in a time lapse, very rapid time lapse, thousands of different situations, understanding the drivers for how the web's formed. Very intriguing, yeah.
Yeah. Also, like, you know, the web is something which it never stops. You know, it's not a finite element. You know, well, I mean, the spider is all the time fixing and repairing it and doing and doing and doing. It's a constant thing. You know what I mean? A fly comes, break it a little bit, she goes, she repair it. then usually, you can see there is a kind of a patch somehow. And she come next day, then she put another patch, and then there is a moment that is a little bit too much broken, and then she rebuild it all again. It's something which is all the time kind of work in progress to a certain extent.
That's fascinating. Next question. Sure, here, and then we'll come to the other side.
Sorry.
That's okay.
Yes, thank you. Yeah, we've been in a discussion together with Thomas and Evan Saporin about this question of sonic realization. And I found it interesting what you said earlier, in the sense that humans cannot sense tension maybe in kind of cables, and that possibly, since the spiders are, they're blind, they cannot hear, and they're sensing obviously some movement, and we use words because we want to speak about, music, and then we have to use a terminology like vibrations. So I'm wondering how much is known actually about these vibrations. I mean, when we speak about sort of a cable system or a string system, then there's kind of longitudinal and transverse vibrations. We know that it swings. We see it gets deformed. Does it continue? Is it, is it passing through the cable, so to say, of the web? And do we know about obviously hyper-developed sensory abilities of the spiders to through this movement, to sense vibration and distance?
Yeah, I think that's a great question. We think that the spider has an ability to process all the data it generates from these thousands, maybe millions of hairs and sensors, and make sense of the world around it in a way that we have, 2 hands and 2 legs, and we can sort of touch things. The spider has other abilities, and so they might be able to reconstruct forces and deformations in ways we're not able to do as humans. And actually something that we can use in engineering if we're interested in understanding deformations and breaking and repair of bridges and structures, in using sensors and understanding those kinds of behaviors and patterns.
Sorry, before we use the word vibration, is there really a vibration as we would describe it as a physical property? Has it been measured?
Right.
Can one look?
It becomes more complex. Yeah.
Are there waves?
When you vibrate, when you excite one of those pieces, right? You can see sort of very complex combinations of longitudinal and transversal and shearing. One of the things we've been playing with is to understand the wave, how these waves propagate actually in the web, because it's not a continuum. It's not a single cable. It's this intermediate density complex structure that we haven't studied in detail.
But yes, there are mode shapes and natural frequencies.
Yeah, each of the elements would behave like this.
Karen?
But what's amazing, Zhao was showing me the other day what Markus and Zhao were working together. Even the model they build also, even the property of the elasticity of, it would be interesting for when we start to work together. They really tune it even with one of the silk strength from Black Widow. This means quite precise the amount of elasticity that this model is rebuilt digitally with exactly one of the, they found out with a colleague, no? So
in Brown University.
You can have the elastic property. Sorry. So the elastic property of the every single silk thread here, we constructed actually based on very precise experimental measurement. We have a collaborator in Brown University. So she used the laser spectrum to measure the stiffness matrix of the silk material in different directions. And we also have a full atomistic model of the silk. So based on every single molecular detail of the silk, every silk peptides, and we have compared those results, and here the model we have both very precise description of the elastic property as well as
the density is easier to measure actually.
So you can compare the different types of silk. I think Caroline Jones, did you have a question here in the front? Thank you.
I'm being selfish because, other people also have questions. And I'm going to break Leela's rule because this is a question about the universe.
Dave?
About the universe.
Oh, okay. It's a question about the universe.
Louder. I'm Dave now.
So in the most simple framework that, a child, if you build a web, it's an additive process. You're adding
additive
material. Yeah. You're squirting out of your spinneret, your whatever, right? And the universe is a problem of condensation. So the filamentary structure is condensing, right? So there's a very simple question about how or why these models can be compared. Is it at the level of the quantum that you're talking about? And I mean, do you want to think about strings, like string theory, in terms of this web? Or is it, mostly it feels like a metaphor. Mostly it feels like, this kind of looks like that. No. But in art history, we call that pseudomorphology. So I give you this word, and you can think about this word. So that's the question.
Can I go to the first shot? So I think it's more than that, I think. And we were just beginning to reflect on this. But actually, the condensation is really what's happening in the. If you look at the protein, what happens in the spinning actually is this condensation of proteins that have been loosely connected, and in the spider's body, it's sort of in a homogeneous distribution of a liquid, right? The spinning is this condensation of many protein chains into very, very low, very high density into forming these connections, these secondary structures. So you create out of this more equally distributed amount of material something that has a structure, right? And so now, once you create a few filaments, you condense others to that because the spider will orient itself around this. And so I think there could be more than a pseudo analogy there.
Yeah, and at the same time, it's like this is what we have been discussing with. I mean, I think so. The entry point, yes, is like a very simple. It's like there is not much why. But somehow with Zhao yesterday when we were talking, it's really like now, there are some kind of more kind of intrinsic emerging properties, and that's what we're trying to look, which is not so much like a visual maybe that you can say, well, this looks like this, but there might be some kind of, for example, it's like how many nodes are in space in relationship with the length of every single thread. You know what I mean? Some kind of more deep mathematical relationship that you might try to understand, or how sound propagate in a two-dimensional, one-dimensional, two-dimensional, three-dimensional. Does it mean it's something which might sound correct, or you can tune it somehow because you have some kind of previous knowledge that you might refer to it, but at the same time, I think so we're getting more and more refined somehow, or trying to understand where we are.
Okay, next question, sir.
Thank you. Markus was commenting on this idea of looking at cross scales and how there can be resonances and evoking from one level to the other. I know one of the works that Tomás has done that we're trying to replicate now with the Red Cross of from one plastic bag, one person, one house, all the way to making a solar hot air balloon at the neighborhood level, all the way to the global level when the Museo Aerosolar travels around the world. In this question about individual versus social spiders, could you tell us about the human creatures that were looking at your big representations of these spiders? How did they relate to that installation? Was it mostly an individual looking at one segment, an individual looking at the structure and function? Was there interaction between people when looking at this? Is there room for designing an interactive endeavor of some kind next time you do something with spiders? It's just too much fun to think about it. I wonder what you're thinking.
No, the first thing what I could tell you is the female world. No, the males are minority and kind of useless and do nothing. You know what I mean?
Are you talking about the spider world or the human world?
I think so. We can drive some conclusion in the future if we want to survive. I think so. We should. This means usually spiders are always 8 female, 2 males. This means that's a huge majority is a female world, and the male really mostly also do not do the web. Most of them, they're very small, and the story of the black widow after mating, you can eat it up and throw it away.
It's a good protein source.
Does it mean? I don't know. Well, it was a funny analogy, but maybe Markus can get more to the point.
But just in general, as people react to your installations, do people tend to?
No, I'll tell you another. For example, when he's in the Cytophora, which is this kind of semi-social, no, the male, there is a moment that they want to mate, and he come on the kind of he's still territorial. It's kind of somehow there is a kind of orb web, but it's a little bit more complex. And then when he comes on the side, and then he's really kind of start to vibrate the web in a certain fashion that the female, which is kind of here, she recognizes it's not a fly. No, because she's blind, she cannot see it, it's a male. And then he come and then a ping, 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 he really pitch some of the strings that somehow it really, and the female for 1 hour let it play. And the male it go there and a ping, ping. He lose 60% of his own body weight. So much exercise. After 1 hour, the lady say, okay, come on, they mate. She eat half of the man. After he goes away, plays a little bit with half body, and then again, and then it's over. But it's a quite effort to seduce.
So he was thinking about how humans reacted to your webs, but that was so much better. I think we should stay with that. John Durant, and then.
So this is a very basic question, but Thomas has just, made it impossible not to ask for me. I had been thinking that the missing element in this collaboration was the biology. I mean, we have an artist and we have an engineer, but the more
musician.
But the more that Thomas speaks, the more I think that you are a biologist. You seem to know a huge amount about these spiders. So I'm interested in the backstory there. How did you get to know so much about spiders, and are there any biologists in this interdisciplinary mix?
No, absolutely. And this is what we just have been talking before with Markus to try to kind of set up the team all together. There are two persons which mostly I work in Frankfurt together. One is Peter Jäger. He's at the Senckenberg Museum in Frankfurt. He was at the beginning the world leader of the Arachnology Society, and then now is Yael Lablin from Israel, and then she also. And both of them, like the arachnid and mostly it's very, very small. There are not so many people who study spider webs, because also there was not really a method how you could scan the three-dimensional webs. You know what I mean? This mean now it's kind of maybe. These are the two persons which we work most, and also you cannot buy spider. This means you really need friends around the world to, you know what I mean. The social spider is really. I mean, you can only buy in Germany so far is like the black widow and a tarantula. Most of them there is no market. This means if you got 43,000. Now we are planning to go to Ecuador and pick the social spiders that are more complicated. There are only 20 species, you know what I mean. And this means for example, Yael was shipping some stereodiffus spiders to the studio. Peter usually got who is bringing some. This means it's a great collaboration about. And with Markus also, when we think now that we would like to, and without to send spider to the ISS, to the International Space Station. The selection of the different interests each of us might have also is really, at the beginning, is pretty much based on the arachnologists, because, they have to survive the journey. This means they have selected already some kind of species that they could think, and then we are sharing with Markus, and I'm also thinking, and, we will decide all together which are the candidates, astronauts, spiders.
Thank you. And just here at the back.
I'm interested in this as like an artistic and a like materials type of thing. Have you considered like coming up with some sort of resin or something that simulates the silk to perhaps 3D print or something like that? Is that something you're looking into?
Yeah, we've done. I think we showed a slide, but yeah, we've 3D printed webs, only two-dimensional webs so far. And we're trying to recreate, actually, this web that we have, we're trying to recreate and 3D print that web also.
And that's with a synthetic silk that you've developed or worked with others to develop?
So we can do both. We can actually, we have two ways of doing this. We can actually create filaments synthetically of actual real silk that we have genetically recreated in the lab completely. That's one way. The other way would be what you described, using a synthetic material like PDMS or silicone or something like this. And that is easier, right? But both ways is possible.
One fascinating thing to point out is that if we use 3D printers or other more advanced materials that we develop, those require a large power source. And you think of the spider doing this with a few flies a week as a power source. So we're not there yet.
Right.
There was a question here.
As an architect, I'm always looking for a way to do a curve less expensively, because most building materials are straight, but people feel curves and they're more natural. So this would obviously have a lot of application to tensile structures. And my question is in your model, are all the spiderweb filaments straight lines? Because it's a force diagram, right? Each one is, and they connect together, and there's a force at each intersection, and you've been able to model that. So you could have a fabulous time with different light intensities at each intersection related to the force of that, or color on the spectrum. Maybe you probably that's what you're working on, right?
That's right.
And think of that in a building or a tensile structure.
Exactly.
The wind blows, and you'd have these incredible light shows by you know.
That's a terrific idea. Yeah, I mean the wind is something we've thought a lot about actually today, and actually creating maybe it goes off your question a little bit, but creating gravity-free environments on Earth by blowing wind, sort of to mitigate the effect of gravity, which pulls the spider down.
Yeah, that was my next thing. Is gravity involved in this or at all? If it's all intention, gravity shouldn't have anything to do with it. But when you invert a web, do they sag?
There's I think there's a directionality with this. But the question about the light and so forth, yeah. I mean, we thought about having actually humans go in the web and they would play with the web. You would try to pull on the web and try to experience, and you would have light and colors and maybe audio signals to get another dimension in the experience, which you usually don't have, right? You don't really.
Giant spider comes out and eats
you. No, maybe to add about because no, the other thing which is a little bit which goes in that direction. A spider, how they travel. It seems that the spiders are the animals who could fly higher than any other, or almost there. Yeah, how you could think is, I mean, it start to give us some chances about maybe we might be able to fly in the future. But anyway, that they are, you think like they are not morphologically developed to have wings, to be able to fly. But, the spider do a method which is called ballooning or kiting, no? And then they cross all the way from the Mediterranean. They come from Africa to Europe without any visa, all the time. They are like with they kind of release the thread on flight, they hatching. It's like the Charlotte Web, like they kind of, and then the wind it blow, and then when the stretch is long enough, they kind of release themselves and start to fly. I mean, they cross very, very high, and then how they fly, is like with the thermics, the currents are, the wind, the blow, and they get very, very high and they cross. I mean, it will be interesting. And there was a kind of a big question about, because they find out that there was a spider which was quite big, I don't know how many grams, and they measure, they say, okay, how much is the line, one of these threads, how long have to be for this spider to take off? And end up was 800 kilometers for one this piece. And this means all the scientists could not find out how, one single thread, 800 kilometers, because of the drag, that you need, how. And this means what they find out is actually what they do. You can correct me, and then it's half fiction, half no, what I say. But this means they come up here, it seems, and then they start to release together. No, there is one here, one here, one here. They start to release, the air start to blow, and then how they do, they release a piece of thread which is without glue, and then they put a small glue. Then again, another piece of thread and a small glue. They make a line with glue points. You are here also, and then you start to release the thing. And this means the air, and the atmosphere, and the thermics, and all the wind, it kind of start to weave a web in the air. And then this web, when you have a mesh and something which is a little bit like, imagine a parachute, a paragliding, with this it make kind of a structure, and then They can take off all at the same time. This means it's fascinating, this idea of making a web that is built in the atmosphere and became ballooning. Anyways, but it's true, eh? You can read it.
That's fabulous. It's mostly true.
Today I got validation with MIT. You should trust me now.
We have time for just one or two more questions. Here and then here.
I'm sorry, but actually I have some comments related to the question.
I get it.
Yeah, just quickly, please.
Just quickly. Yeah, so Thomas and I actually we discussed about the how to design those human scale architecture. So use this kind of method. Actually, we can design the boundary condition for this complex structure. So we can optimize the boundary condition, and we can actually manipulate the stress distribution in the network, and then we can test how much. I mean, what kind of optimized structure can take impact force or wind loadings or any kind of those design to better have a better performance.
Yeah. I see. Thank you. So I think there's a question here in the front.
Yeah. I was just wondering, in the simulations, I get how you get the geometry from the picture, but how do you know how much tension all the strings are under? Or how, yeah.
Well, in the beginning, it's purely point-based geometry, and we connect the points. There's no initial tension in the system, other than maybe some little pretension, but there's no other measure of tension in there. We don't have that information. You're right, but it's not in there. Yeah.
So they're linear springs, basically. And there was there was one in the back, and then we'll take one last one here.
No, maybe Caroline, one thing which I'm also thinking, because there was all this thing about biomimicry, no? It's like a kind of this simulation. But this is what I think, so Markus is really getting to the next level, no? Which is not biomimicry, biomateriomics, I think this is really kind of an evolved step into understanding, some kind of emerging properties on kind of.
So to make a universe.
To make a universe.
Yeah,
to imagine a new.
But it's a little bit, it's a little bit more.
I see. It's not just mimicry. Okay.
Yes, my question begins with Thomas and then moves over to Markus. My question is, of what material did you fabricate your construction, and how do you fabricate the individual joints among members? And then the next part of the question is, how does that translate, or has that been translated into your computer model, and what effect might it have?
Yeah, I mean, this is what we were discussing with Zhao and Markus the other time. The Black Widow in this case have 7 different type of. And then our friends arachnologists might cover much better than me. But anyway, I supplement them here. But the Black Widow have 7 different type of threads. I don't know which is the degree of elasticity of each of them. I know that, for example, usually the vertical ones. The model is always upside down. No, this is up and this is down. For example, this one usually is always have some kind of glue in the bottom. Does it mean it might have a different, and does it mean the model, how I built it myself, every thread was kind of a non-elastic, but the joint and the node where everything connected was elastic. Does it mean it gives me some margin a little bit to correct a little bit? But because if I have everything elastic, it was moving too much. Does it mean I built, the segments are precisely, they have to arrive from here to here, and the node it was built with an elastic. With Zhao, well, and Markus, we were, I think so. We put only one property, everything
is elastic. Yeah. I mean, the connections are perfectly glued together with the glue silk. So it's different than the web that you constructed. You have the elasticity in the nodes. We had elasticity everywhere in the system, which is probably how it would be in a real web. Yeah.
Okay, let's just have one last question here in the second row. Right here, Meg.
Yeah, I have a structural question. It's kind of a follow-up to his question. How much can the model tell you? Could you analyze it and figure out what would make it fail? I mean, it's so complex. Do you know enough to use? Have you located things in space, or if you don't know what the tension would be on various things, to what extent could you analyze that structure?
Yeah, I mean, in the 3D web, in the 2D web, we've done exactly this. It's a lot easier in the two-dimensional web, right? We've removed individual struts, and we've identified what are the conditions to make the web break very easily versus being very resilient. In the 3D web, exactly one of the big questions we're trying to answer is exactly that. Is it by removing random struts, or is it by removing them in a particular pattern? And to answer that question, we can do this in a simulation. We can do it much easier than in a real web, because we can do it in a real web, or in the installation we have to cut the cables. And so the model is a great way of doing this, and we can do it in using inverse algorithms, using mathematical models that would either randomly or using genetic algorithms selectively, progressively remove particular threads that are highly loaded and deformed. So there are ways of doing this mathematically that we can apply to identify the failure modes to make it fail, and conversely understand what makes it robust. Yeah.
Well, this has been tremendously fun, and I think it's a testament to the strength of both the arts and science and engineering research at MIT that so many of you would come out on Thursday night for is today Thursday?
I asked the same question.
And I personally, it was a privilege for me to be here and to take part in the conversation. I've enjoyed learning from both of you. And these two rock stars, I think, will stick around for a few moments. So if you have a few other questions, please come and say hello. Thank you all so much for coming, and thank you for hosting us this evening.
Thank you. Thank you.